Hello everyone. The next topic in this fourth module is performance of demand paging. In the previous video we have seen how we implement demand paging, means what is the need of demand paging, how page fault is implemented. Now we'll see what is the performance of it, and then we'll be seeing what is copy and write a topic. So performance of demand paging. Before going that, stages of demand paging at worst condition. Worst condition in the sense, if there is no page found in the main memory, then a worst condition occurs. What if the page is not found in the main memory? Then we'll see how this demand paging works. So this was our fault, like page fault management. So in the same way demand paging works. So trap to operating system will be generated. Save the user register and process state. So trap was generated, the state of a process and user registers is saved for next, means if the page was not found, then the process will be going for wait condition before going to change the process state. Just save the process state and then change to next process. Determine that interrupt was a page fault. So the trap, we have to determine it as a page fault. Check the page reference was legal and determine the location of page on the disk. So we have many types of fault. In that, one was page fault, but we had one more fault called illegal access for the page. Means the page what you were accessing does not belong to that process what you are executing. If it is not, then means we have to make sure there is no illegal access, it was a legal access and it was page fault occurred. So issues a read from the disk for a free frame. What happens? Wait in a queue for the device until read request is served. Wait for the disk seek or latency time. Begin the transfer of a page to the free frame. So you have to wait for device management in the queue for the read request, then device has to seek and it has to give you the free frame available. Until the free frame is available, you have to wait for the device management. While waiting, allocate the CPU to other user. See here, if the user was waiting for some other data, like here it was waiting for device management, this CPU has to be allocated for other process or other user in the sense. Then receive the interrupt from the disk input output subsystem. So once a free frame is allocated by the disk management to the device what you were waiting, get the device, means get the free frame, allocate your frame from the secondary storage device and copy it back to the main memory. We call it as swap in. Then save the register and process it for the other user. Since you were in waiting state for the demand page, process was executing for another user. That user process state to be saved. Determine that interrupt was from the disk. Correct the page table and other tables to show the page is now in the memory. Once you get the page from the secondary storage to main memory, your page table to be updated, then you have to add the frame number, means corresponding frame number for the page number. Convert your invalid bit to valid bit. Wait for CPU to be allocated for the process again. Since the process was executing, like some other process was executing when you were doing page fault management, you have to wait until your CPU is allocated to you. Restore the user register, process state, new page table. Resume the interrupt of the instruction. What and all you have to restore is user register, means user informations, process states, means process control block to be updated process control block informations, new page table. The old page table was having page fault and you have updated your page fault, so new page table to be loaded. Then you have to start your instructions, like continuation of instruction and execute your process. So continuation of this, we have to find, we have three major activities: serving the interrupt, read the page, restart the process. To all this we have page fault rate. So we count page fault rate, which is in between 0 and 1. If it is 0, then there is no page fault. If it is 1, what and all the pages you get is page faults. So based on this value, you have to find page fault rate and effective access time. So effective access time in the sense effective access time for a process under execution for memory access. So if you get 100 milliseconds of memory access, then it is counted as efficient. Means if there is no page fault, like if you consider this formula, so you are adding memory access time with page fault. What if your page fault is 0? P into 0 becomes 0 and only you get memory access time. So it has higher access time with no page fault access time given. If it is 1, means complete page fault is added to this. You have 10 instructions or 10 pages to be added. 10 into 1 will be having 10. So 10 times your memory access time will be delayed and effective access time will be very less. So we'll see with an example of demand paging for effective access time. Memory access time, consider 200 nanoseconds for each page. Average page fault service time is 8 milliseconds. So for every page fault we have 8 milliseconds of access time. So here this is milliseconds and this is nanoseconds. Don't get confused. For page fault it is using 8 milliseconds and for memory access it is using 200 nanoseconds. So 1 minus p into 200 plus 8 milliseconds, which is 8 milliseconds of data. Means 8 milliseconds. From 8 it is given as 80 lakhs. Means the point is converted to 80 lakhs since it is 80 milliseconds, means 8 milliseconds. 8 into 10 power 6. So p value is constant. We don't know the p value, so keep the p as it is. Then convert this 1 minus 8000 means 80 lakhs with 7 1 into 200 p into 200 plus p and this value. So 200 into p, 200 plus p into minus 8 milliseconds with 200, you get this value 7999800. So this 8 point, if one axis out of 1000 causes a page fault, then 8.2 microseconds means efficient time access will increase to 8.2 microseconds. This slowdowns the factor by 40%. What if your page fault or the performance degradation is less than 10%? What happens? Then the page fault, like for 200, if it is 10%, it is 220. For 200, 10% is 20. So 220 is greater than 200. Yes, if the performance is 10% greater, and then 220 is greater than this. So if it is 10%, like performance degradation is less than 10%, then page fault will be 4000 page fault is for every 4000 it's 4 lakh memory accesses. Here the page fault was occurring for every 1000 times. Here if you decrease by 10%, it will go for 4000 4 lakh instructions. For every 4 lakh instruction, one page fault will occur, but here for every 1000 one page fault was occurring. So next topic is copy on write. Copy on write is a method where if you are sharing, if we have parent and child process, consider that if you are sharing the instructions or sharing the pages in process, if you consider parent and child process which is sharing some pages, unless and until there is a written function done for the page, unless and until the page is rewritten with some data, then only a copy of that page is copy of that page will be maintained. If not, it shares the pages without copying it in two ways. Like if you have one parent and one child, it accesses 3 pages, it is sharing 3 different pages, it will be shared unless and until copy is written to the page. So here we have v4. It's like variation of fork, which is similar for the fork, but it uses copy on write address space for the parent. So if you use this, designed to have a child call execution, very effective than normal fork. Like first we'll see how it works. So before this, like before modifying any data, process 1 and process 2, consider process 1 as our parent, process 2 as our child. So process 1 and process 2, parent process and child process, is accessing 3 pages here: page A, page B, page C. Until the process is modifying the pages, like consider we are using a page C which will change, when it is executing. Unless and until it is rewritten, the pages will be shared. What if it is rewritten after a process 1 modifies page 3? So process 1 is using page A, B, C, but it has modified page C. Then a copy of page C will be stored and the process 2 will be accessing to this page C. What if process 2 modifies the page C? Then this page C will be remain same, and page C, like one more copy of page C, will be given to process 2 if it is child. If it is parent process, then a copy of page C is given for the parent process, and this page C will be used by some other process if it is shared. If not, this page will be considered as free space, since there won't be any reference or reference link to that page in the page table. Okay, so this is how modifies, like copy on write, work. We'll go back to copy on write. Now you can understand what vfork is. Instead of calling a process with fork, call it with vfork. Then the child process can use the shared data on copy on write method. Copy on write address space for the parent, like parent will be given, designed to have child call execute. So the process child can also call execute, and it is very effective for changing the value by the child process also. Understood? So I hope you understood the topic. Thank you.